Hello, my name is Daniel Ordnung. I work at KU Leuven on improving the surface quality and mechanical performance of parts produced by laser powder bed fusion. And today I'm going to present you a novel method to improve the fatigue performance of parts with an inclined surface. I will start with a brief introduction, why the quality of inclined surfaces is challenging but also important for fatigue performance. Then I'm going to present you a technique we recently developed in our team, which is called in-situ laser remelting and enables us to improve the surface quality of inclined surfaces already during printing. In the results chapter, I will discuss the effect of in-situ laser remelting on the fatigue performance. So why is the surface quality of inclined surfaces important for the fatigue behavior? In additive manufacturing, there are different factors which have a limiting effect on fatigue behavior. One factor is the high surface roughness of additively manufactured parts. In particular, when we look at inclined surfaces, we see different effects which lead to a high surface roughness. There's the intrinsic staircase effect due to the layer-wise manufacturing, and then on the other hand, there's the edge effect, meaning elevated edges. These two effects are combined for inclined surfaces, leading to a high surface roughness and making them very critical for fatigue applications. In our team, we developed a technique which enables us to improve the surface quality of inclined surfaces already during printing by in situ laser remelting them. And the question for this research is, does remelting improve the fatigue strength? The difficulty to improve the surface quality of inclined surfaces already during printing is that they are actually covered by powder due to the layer-wise manufacturing process. And thus it's not possible to laser remelt them. The only option is to laser remelt them as a post-process. We use a pulsed wave laser to scan the solid part surface. And the high-intensity laser pulses interact with the solid part surface, vaporize the material, and induce high pressure waves, also called laser-induced shock waves. These laser-induced shock waves lead to a powder bed disturbance around the part, and we use that disturbance deliberately to blow away the powder from the inclined surface. And thus, in a second step, it's possible to access the inclined surface and laser remelt it. So far, we could see that the powder removal process, followed by the laser remelting of the inclined surface, leads to a surface roughness reduction of up to 60%. The aim of this study is to improve the fatigue performance by laser remelting inclined surfaces. Therefore, we manufactured samples by laser powder bed fusion and processed the surface by this in situ laser remelting technique. To have a comparison, we also manufactured reference samples in as-built state and samples which were afterwards processed by EDM. We used merging steel and titanium alloy powder and processed it with a special dual laser machine setup, which I will explain on the next slide. The samples were characterized with a focus on the roughness and the microstructure. Therefore, we used common optical and tactile measurement instruments. The fatigue performance was tested by 3-point bending tests. The samples were loaded by a sinusoidal compression force and at a constant frequency of 30 kHz. As I mentioned before, at KU Leuven, we used a special dual laser machine setup. This setup consists of a common laser powder bed machine hardware, which is equipped with a continuous wave laser. And additionally, there's a second laser. This nanosecond pulsed laser can be used for laser ablation-based processes, as in this study, the powder removal process. The fatigue samples were manufactured by laser powder bed fusion, and after building, the inclined surfaces are covered by powder, and therefore it's not possible to laser remelt them. Thus, we applied the powder removal process, which is illustrated here in the video. So you can see the pulsed wave laser starts to scan the top surface, and by a reaction, shock waves are created. These shock waves interfere with the powder bed and blow away the powder from the inclined surface. We developed a special scanning strategy which allows to very efficiently clean inclined surfaces from powder. Here, this process is repeated incrementally until the laser reaches the bottom part of the inclined surface. At the end, the entire part surface is scanned again by the pulsed wave laser to get rid of last powder particles. And as you can see, the entire surface is clean of powder. And thus it is now possible to actually assess it with the continuous wave laser to laser remelt the surface. In the video you can see the continuous wave laser starts to scan the inclined surface and repeats that several times until a shiny polished surface is reached. In this case, the surface was scanned 4 times and it ends up with a very shiny surface here to see in the picture. For the sample characterization, 2 factors were mainly important. On the one hand, to measure the critical cross-section, and on the other hand, get a 3D surface measurement of the curved area to determine the areal surface roughness. The fatigue tests were done by 3-point bending test until failure or until 2 million cycles. If the sample did not fail after 2 million cycles, it was tested at the next higher stress level. The fractured samples were then assessed by SEM imaging. Results of laser remelting. So first of all, the laser remelting process has a very visual and clear effect on the surface texture. When we look at a 3D surface measurement, we can see that the remelted samples show a very smoothened surface compared to the S-build. And this is actually confirmed when we look at the surface roughness values. For merging steel, the surface roughness was reduced of about 47%, and for titanium it was reduced of about 43%. Another effect is when we look at the microstructure. Here in the top picture we see the microstructure of the S-build sample. It shows the martensitic cellular microstructure for merging steel with its melt pools and the melt pool boundaries. In the bottom picture we see the remelted sample. Here in the bulk material, the microstructure is similar, but if we look closer at the top surface, we see a concise remelted layer of about 50 micrometer thickness. This layer shows no traces of pores or lack of fusion. The fatigue performance of the laser remelted samples can be seen in the plots on the left side of the slide. In the first graph, we see the results for merging steel, which was tested at factor 0.9 of the yield strength. At this lowest stress level, the S-build samples failed at around 100,000 cycles, while the remelted samples and also the EDM samples withstood 2 million cycles. These samples were then tested at the next higher stress level at factor 1.2 of the yield strength, and here the EDM samples failed very early at around 50,000 cycles, while one remelted samples again withstood 2 million cycles. This sample was then tested at the next higher stress level again and failed at factor 1.2 of the yield strength. Similar can be seen for the titanium samples. Here at the lowest stress level of factor 0.68 of the yield strength, the S-build samples nearly failed immediately after around 30–40,000 cycles, while again the remelted samples withstood 2 million cycles. These samples then failed at much higher stress levels at factor 1, 1.2 and even 1.4 of the yield strength. The significant improvement of the fatigue performance in 3-point bending test of the remelted samples can be on the one hand explained by the surface roughness reduction. But on the other hand, if we look at EDM samples and remelted samples, we see that the remelted samples performed much better in the fatigue bending tests, even though they have a higher surface roughness. So this clearly indicates that not only the surface roughness reduction, but also other factors are beneficially impacted by the laser remelting process. One explanation could be connected to the modification of the subsurface microstructure. Here it needs to investigate it more and further if the laser remelting, for example, induces compressive stresses which have a positive impact on fatigue performance. Here we can see the first results for the fracture surface of a remelted maraging steel sample. We mainly can distinguish two fracture zones. There's the crack initiation and propagation zone, and then we see the final fracture zone. The final fracture zone shows dimples, which is a typical sign for a ductile fracture behavior. When comparing the fracture surface of the remelted sample with the as-built sample, it appears that with increasing stress level where the samples failed, also the fracture zone, the final fracture zone, increased. In situ laser remelting inclined surfaces appears to impact different factors in a beneficial way for fatigue performance. On the one hand, the laser remelting leads to a significant reduction of the surface roughness, for maraging steel of about 47% and for titanium alloy of about 43%. On the other hand, the laser remelting process modifies the subsurface microstructure. Here we could see a remelted layer of about 50 micrometer thickness, which appears to have a beneficial impact on the fatigue behavior. In the fatigue 3-point bending tests, the samples which were remelted showed a significant improvement. At the same stress level, they withstood it several cycles longer, while they failed at much higher stress levels. For future work, it will be interesting to investigate more what the modified subsurface microstructure has an impact on the crack initiation and the fatigue performance. Also, it will be interesting to upscale the technique for industrial applications. At the end, there's only to say thank you. Also, thank you to my colleagues and as well to you that you stayed until the end of my presentation. And I hope to see you soon in the future at a real-life conference.